representation theory of p-adic groups.
Thank you very much for the invitation. Okay, so this is my title. So the motivation behind understanding this smooth representation theory is the local Langlands correspondence, which I'm going to briefly mention probably at the end of this lecture or at the beginning of tomorrow's lecture. The so-called classical Langlands correspondence deals with the p-adic, or let's say complex representations of p-adic groups. And more recently, a mod p component, mod p and p-adic component of this Langlands correspondence has been developed. And I'm going to say a few words about the mod p aspect of it. So the R will be the field of coefficients of our representations. And it will be either C or a field of characteristic P, and I take it algebraically close to avoid the problems. So at this point, I'm going to recall really elementary fact. At least, I mean, today should be very elementary. And my goal is to explain a little bit why the mod p representation theory and the mod p Langlands correspondence is still barely developed, even if it started more than 10 years ago now, around 2000. So the reason is that there are so many problems arising in the mod p representation theory, and I'll try to point out a few. So what is our p-adic group? Let me define first our p-adic field. So I'll give a few notations. So F will be a locally compact, non-Archimedean field with residue characteristic P. O will be the ring of integers. P, the maximal ideal of O. And the residue field has Q elements, where Q is a power of P, since we chose residue characteristic P. That's it. So for example, you can think of F equals QP, in which case O equals ZP, P is PZP, and the residue field in this case is FP, or a finite extension of QP, and then, well, all this will depend on the finite extension that you choose. And another case is the field with positive characteristics. In this case, the ring of integers is this. Maximal ideal is this. And the residue field here is FQ. Okay, so you pick your favorite example and you can use it. Until I really talk about mod p representation theory, I won't differentiate between those fields. So who is our group? Well, the G will be the group of F points of a connected reductive group. And our goal is, as I said, mostly to understand why things are different mod p than the complex case, so I don't really need a complicated group, and I will just pick G equals GLNF. And often our examples will involve n equals 2. There. So what does it mean, smooth in the title? Well, a smooth representation of G is a representation V such that all the stabilizers are open. So we need to understand a little bit of the topology of G. And, well, already, for example, of the topology of QP. So QP, the completion of Q for the p-adic norm, which is ultrametric, multiplicative. So QP is totally, is locally compact and totally disconnected, because you can write a fundamental system of neighborhoods of 0 given by the p-I-ZP where ZP, well, we already defined it, but the ZP is the one radius ball. It's compact. Okay, and PZP is the open one radius ball. Okay, but that's for ZP. We're more interested in, QP. We're more interested in QP star because QP star is GL1. So let's look at the smooth representations of QP star. Well, QP star is also locally compact and totally disconnected. We can even say it's locally a pro-p group. It's a fundamental system of neighborhoods of 1 is given by the UI, where UI is 1 plus p-I-ZP. And you check that UI, the quotient, is a p group. And by the way, ZP star, which is the unique maximal compact subgroup of QP star, satisfies ZP over U1. U1 is a cyclic group with p minus 1 elements. Okay, so what is the character of QP star? So, smooth characters, meaning smooth one-dimensional representations of QP star, which ends up being just a character from QP star to C star with open kernel. Well, phi is determined by the value at the uniformizer and its restriction to ZP star. But then we know that the kernel has to be open because we decided we were interested in smooth representations. So there is a certain I, 0, I guess, or 1, defined after 1, such that phi restricted to UI is trivial. Okay, so so phi factor is true. So that's whole factor is true. Okay, and the I that will be involved here, the smallest possible I, will be called the level of the character in question. And if phi happens to be trivial on ZP star, the character is called unramified. Okay, if I want to do the same thing now over FP bar, QP star to FP bar, I start the same way. Well, phi is determined by its value at the uniformizer and its restriction to ZP star. ZP star is, we say that it's a cyclic group times the pro-p group. And again, well, there is an I, because it's a smooth character. There is an I such that phi is trivial on UI, on 1 plus pi zp. So basically, we are interested, so phi factors through, the restriction factors through, restriction of phi to 1 plus pzp factors through a p group. So here I could conclude right away because I'm just dealing with one-dimensional representations, but let me state a lemma that we'll use later. And this is simple, represent counting arguments. A p group acting on an FP bar vector space, or just a vector space over a field with characteristic P, has a non-zero fixed vector. As a consequence, the restriction of phi to this P group has to be trivial. So phi is trivial. So it seems that there are not so many characters. There are not so many characters of QP star with values in a FP bar. Not only there are not so many of them, and it seems that they are quite easy to list because, well, they are all tamely ramified. And this is going to be kind of the general philosophy that at first sight we will think, oh, okay, mod P things are going to be easier because there are fewer objects and they're easier to classify. But we all know that the homological properties of the categories in modular representation theory are harder, so there will be things to say. Okay, so that was for GL1. And what about GLN? A little bit of, describe quickly its topology. Okay, now GLN. F, or let's say n, greater than 1. Well, it's also locally a pro-p group, and we can describe explicitly, again, a fundamental system of neighborhoods. First, K, the GLN over the integers, is up to conjugation, the unique maximal compact subgroup. And it's open of G. Let's call this G. And it contains the congruence subgroups for I greater than 1. Okay, I didn't introduce, oh yeah, okay. Mn of I. Okay, this is also open and compact, and the quotient is a p-group. And the Ki, give a fundamental system of neighborhoods of 1. Okay, so as we noticed here, it was important that we had a big pro-p subgroup in QP star, and here we also have a big pro-p subgroup, which is unique up to conjugation. And this is what is called the pro-p-Iwahori subgroup. So to introduce it, let me just notice that K over K1 identifies with GLN over the residue field, that this contains a Borel subgroup of upper triangle matrices, which has a unipotent radical, the unipotent upper triangle or unipotent matrices. And we denote by I the pre-image of B in K. And I1 will be its pro-p radical. It's going to be the pre-image of U in K. All right, so I is called the Iwahori subgroup. I mean, this is the upper standard Iwahori subgroup. And I1 is the pro-p. To have an idea of how these, I mean, we have an idea of how these groups act, but maybe I want to illustrate how they act on the semi-simple building of GL2 as an example, and so that we can introduce, I mean, let's say I already introduced the groups, but I'm going to describe them using the tree of GL2. So for n equals GL2, what is called the Bruhat-Tits building, or the semi-simple building of G, is a tree. And how do we construct it? Well, the vertices, what are they? They are the lattices of F square. And I pick a canonical basis, or let's call it B, B1, B2, up to rescaling. Obviously, G acts transitively on the lattices. So I can pick as an example X naught, the vertex corresponding to the class of, well, the most obvious lattice. And we know that its stabilizer in G is, well, contains GL2O and also the center, because everything is up to rescaling, where Z is the center of G. So we just said basically that the set of vertices is in bijection with this set, these cosets. Okay, so how do we decide if two lattices are neighbors in the tree? Well, not two classes of lattices. So let's take y1, y2, two vertices, and they are neighbors if there is a lattice L1 and a lattice L2 corresponding to each vertex, and such that L1 is contained in L2, and which contains pi L2. This means that L1 over pi L2, well, let's say, it's contained in L2 over pi L2. Sorry, pi is the uniformizer. I didn't mention pi. So what is this? This is, well, this is fq squared, and this is a non-zero subvector space. And it's not the whole space, so this is a line in fq squared. So this means that finding a neighbor for y2 consists in picking a point in the projective line over fq. So y2 and any vertex has q plus 1 neighbors. Okay, so I have x naught that I already chose here, and it has q plus 1 neighbors. I'm going to draw everything for q equals 3. And each point corresponds to a point in the projective line, so I'm tempted to call one of them x infinity, and the other one x1, x2, x3, but then it continues. Everybody has q plus 1 neighbors. Okay. What about the edges? Well, the edges, I can single out this edge. I call E infinity. And I'm going to decide that this vertex here corresponds to the lattice built on the canonical basis, but corresponding to O and pi O. D2. So E infinity, if you do this by hand, you can check that the stabilizer of E infinity, well, it contains this Iwahori subgroup that we described over there. But in fact, it's a little bigger. It's generated by the Iwahori and certain matrices that normalizes the Iwahori subgroup, this matrix. All right. And in fact, the group G, I mean, this can be for GLI and can be proved by very elementary methods. G acts transitively on the edges, which maybe we'll have time to say this at some point. In fact, is equivalent to the fine Bruhat decomposition of G. All right. I think this was it. Yeah. I also wanted to point out that these concurrent subgroups that we introduced, the Ki, can be also kind of read on the tree because K1 fixes the one radius ball of the tree and what's inside, and K2 fixes the two radius ball fixed by K2 and so on. And lastly, because we will have to talk about supercuspidal representations of the group, so we need to understand what is parabolic induction. So what can we say about parabolic subgroup of GL2 when we read that on the tree? Well, we notice that what is a path? What does it mean to choose a path like that up to, I don't know, whatever that means, infinity over there? Well, the first step was to pick a point in the projective line. So in there, I could choose infinity, or I could choose a point in Z mod P. And then to the next step, I need to pick another point in Z mod P, sort of, meaning that when I pass from here to here, I chose a point in Z mod P square, and so on and so on. But we didn't say before, I said that ZP is compact because we could see it as compact when we described QP at the completion of Q, but this can be also obtained as the projective limit of the Z over PIZ, which tells you that a point in ZP can be described by making these consecutive choices that I just described. So in fact, a path at infinity gives you a point in, well, a point in ZP if I start going up, or a point in the projective line over QP if I allow myself to also go down. So in a way, the boundary or the compactification of this tree consists in adding at the boundary the, let's erase this, the projective line over QP. So that's an opportunity to introduce the Borel subgroup of our group GL2. Okay, so the stabilizer of a point in P1 QP is a Borel subgroup. Of GLG here, G equals GL2, and we will single out the upper Borel subgroup, which is a stabilizer of the first, it's just 2 points, of the line generated by the first vector of our canonical basis. Okay, so that was kind of an introduction. So what is our goal? Our goal is to explore, or say a little bit. I mean, I won't explore. I will say a few things about the category of smooth representations of G, let's say GLN or even GL2, over the complex numbers, and compare it, or as much as we can, with the category of smooth representations of G over FP bar. I want to say a few things about their homological properties. And as far as I can, from this very algebraic point of view, I would like, again, to hint at the fact that things get very intricate here, and there is a reason why the mod P Langlands program has been, I mean, there are many reasons, but here we might see a few reasons why the mod P Langlands program has been so far developed only for GL2 QP and not for other groups, not even GL2, not really for GL2F yet. I mean, there are some results for other groups, but still not enough to state a local Langlands correspondence mod P. So, okay. So what is going to be our tools? Well, first I said that I would talk a little bit about representations of finite groups. Why? Because, well, we said that there is finite groups naturally appearing in G, and since we work with smooth representations, well, a representation can always factor through one of those, I mean, not really factor through, but locally it can factor through one of those open compact subgroups. So the first tool will be the representation theory of finite groups. Finite reductive groups, and in fact, I mean, I will just talk about GL1FQ or GL2FQ. Also, because again, because of these representations of smooth, we're tempted to try to understand a representation either of the finite group or of the p-adic group through its invariance under certain subgroups. So understand V, a representation of G, or even a representation of the finite group via understanding families of fixed vector. The fixed vectors, in W for various omegas. And finally, I said that I want to explore some homological properties of these representations, and I chose to do it via a process of localization of representations. It will apply mostly in the case of complex representations of G via coefficient system on the building, on the semi-simple building, and this is a method due to Schneider and Stuhler. So I said it works mostly for complex representations, and there are a few things that we can say for representations over other fields, and I'll try to mention what happens in characteristic P. There. Okay. All right, so finite groups to start with. I'll call it as much as I can. I will try to remember this bar here so that I talk about the finite groups. And I'm going to explore this aspect of thing that we may want to try and understand the representation via understanding its invariance under certain subgroups. So let omega be a subgroup of G. So in my head, I think of B, for example, or U. And I notice that this space of invariant is exactly from omega of the trivial representation into V, which by adjunction is the same of hom over G of the induction of the trivial character of G, of omega to G into V. This induction can just be, this is just the functions. So here, sorry, here the field of coefficient is still R. It's just the functions over the cosets with right action of G. So this obviously is endowed with an action of the endomorphisms of this induced representation, which is what we call the Hecke algebra with coefficients in R of G with respect to omega. And this can be also seen, if you prefer, as the algebra of convolution over the functions which are by invariance by omega with convolution. Okay, so when studying that kind of objects attached to V, naturally, Hecke algebras appear. So we get a functor from the representation over G into the modules. Right modules, actually, if you use my convention over there. well, sending V onto V omega. So let's explore a little bit what that is, because it's a very well-known object. If we choose B over there, or even U, it's not too hard, but let's do it with B. So I take omega equals B. And then, well, I said that a basis, well, because of this description here, a basis of my Hecke algebra will be given by the characteristic function of double cosets like that. And this is indexed by Bruhat decomposition by the symmetric group. The symmetric group happens to be a Coxeter system with generating set S1 to Sn minus 1, where Si is the transposition I plus 1. And, okay, it's a Coxeter system with a length. Yeah. And then, well, the Hecke algebra is generated by, well, has basis a set of all TW, which is a characteristic function of BWB for W ranging over the symmetric group. And the relation in this algebra are the braid relations. Well, there is a reason why it's called braid. It's because you can also write it as Si plus 1, Si equals Si plus 1, Si plus 1, when you write it's capital S being this, but and whatever. This is the braid relation, and the quadratic relation TSI squared equals Q times the unit in R minus 1 TSI plus Q times the unit in R, Q being the cardinality of the residue field. And this is a famous quadratic relation, and it appears here. So since I'm going to insist on the difference between the complex case and the mod P case. I want to this will play a crucial role, because you see that if R has characteristic P, the element TS is not invertible anymore, because this will become 0. So since this relation is important, I'm just going to say a few words about its proof. On the quadratic relation. Let's say for n equals 2, and in this case I will just write S instead of S1. Well, so we said that an element in the Hecke algebra can be seen as an anamorphism of this thing here, which in the case of B is the functions on the projective line. So this, in our case here, this is functions on P1. So again, if I take Q equals 3, I have Q plus, I have 4 points here. I have Q plus 1 points. An element in the Hecke algebra, in particular this TS that I'm studying, commutes with the action of G by definition. And the action of G is transitive on the projective line, and therefore to understand TS or TS squared, I just need to understand TS square of x infinity. That will give me the formula. But what is TS of x infinity to start with? And by definition, let's say that in this thing here, I chose that x infinity, which is a point in the projective line, corresponds to the characteristic function of B. in this setting here. And Ts corresponds to the double coset BSB, and therefore this is the characteristic function of BSB, which is in fact the sum over all A in FQ of the XA, where XA is, or the other points in the, well, this is all the points that are not, all the finite points of the projective line. So Ts sends a vertex to the sum of the other vertices. So now if I do Ts square, I get the sum over A in FQ of Ts of XA, sum A in FQ of, well, the other vertices. So I always get x infinity plus the sum of the finite points, but not A, of xb, which gives me q times x infinity plus sum over the b different from infinity of xb times sum and I recognize here q x infinity plus q plus 1 ds of x infinity. Okay, so this relation, this is, you can really read it here on something that can be seen as the finite building. I mean, this is not really what it is, but and this will appear again in the p-adic setting when we'll talk about the mod p representations or even complex representations of the p-adic group. So remarks about this Hecke algebra. Well, first, if R equals C, then this is just a deformation as we see, because Q is not 0, so this, we can see that this is just a deformation of the case Q equals 1, which is the algebra of the symmetric group. And therefore, this is a semi-simple algebra. But now if I switch to characteristic P, as I said, the quadratic relation becomes TSI squared equals minus TSI. So we can't really, I mean, this argument, this is wrong. And what can be proved is that, well, okay, yeah, it's a little fast. Let's say it's a little too fast. Let's say that being semi-simple is an open condition, and well, okay. Let's say.
You mean semi-simple over C brackets Q, is it?
Yeah, I mean, it's over C here. Well, it's a semi-simple. Yeah, I mean, my argument is a little too fast. I mean, it goes too fast. Okay, but as an algebra over C, it's a semi-simple algebra as a result. I mean, okay, yeah, all right. In this case, so the algebra, you can check that for n equals 2, it's still semi-simple. I mean, just by chance. Well, this is a two-dimensional algebra, and you can decompose it. This is a direct sum of two characters, what is called a trivial and a sign character. But as soon as n is larger than 3, this is not semi-simple. There are several arguments for this. For GLN, you can start with GL3 and you can decompose it and see that, well, you have 3 blocks and you don't have and you have some indecomposable. And then by induction, it will be true for GLN in general. This is not semi-simple. I mean, I don't get into the details to prove that it's not semi-simple, But what can be proved is that yet it is a Frobenius algebra. It's a Frobenius algebra that is not semi-simple, which implies that it has infinite projective dimension. Well, infinite global, projective dimension. And you can even prove that not only that, but there is even a simple module that has infinite projective dimension. So this algebra is really different from, things are pretty scary when you see that. Its representation theory is much complicated than the semi-simple case. Okay. But let's get back to the complex case and see what we can say, given that we seem to be successful describing, understanding the Hecke algebra. So now I take R equals C here. Okay, so here obviously it's obvious that this is a semi-simple abelian, semi-simple category. The representation, there is no smooth here, it's just a finite group. It's a semi-simple category. It contains as an abelian subcategory all the representations V generated by their B invariants. And you can also do the same. Same with U instead of B, if you want. And I claim that the functor that we found before, we described, gives you an equivalence of categories between this abelian subcategory and the Hecke modules. And in fact, we have the same with U instead of B. But I like to use B because the Hecke algebra is very easy and very well known. Well, what is the proof of that? Well, proof, this functor has the functor sending a module onto what is this? Onto this representation, it looks like that. It's the right module, tensor over the Hecke algebra, as a left adjoint, and you prove that, well, they're quasi-inverse. Proof. It's very explicit. And with the key for that, the key is that if you have a representation W of V, complex representation of G, a complex representation, then you can build the following operator, P, B, let's say B, even with omega it works. This is surjective from V to the space of B invariant, and that sends an element W onto, you average it over, under the action of B somehow. Okay, and the fact that this is surjective will give, this is a key point of this proof here. So here you see that you need to invert the cardinality of B, and you really need to work in a field where the cardinality of B is invertible, so C works fine, and it will fail in characteristic P. Whereas a corollary, all the reducible representations of G with B invariant vectors or in one-to-one correspondence with the simple Hecke modules here, and we can even do it with U instead so that we get a little bit more representation here. And that's something that is always used, and this idea is always there, I mean, most of the time there, when we solve the following very classical exercise. Classify the simple, the reducible representations of GL2 FQ over C. So the first step is to classify the reducible representations that have a non-zero U fixed vector or generated by their U fixed vectors. So what does it mean if I take V be such a reducible representation? I know that V U is non-trivial, but this gets an action of B because U is normal in B, and the quotient of B over U is the finite torus. Is abelian, so there's a character of the finite torus contained in V, and say B. There's a character of the finite torus contained in this space here. I can inflate. Well, first contained in this space. I inflated. So I'm doing a process of parabolic induction into a representation of a character of B by deciding that it's going to be trivial on U. And then I have the following thing. I mean, I just found a non-zero element in from B for chi into V. Which means that my representation V is a quotient of a principal series representation, which is a parabolic induction. Example, if chi is a trivial character, then this thing is just the functions on the projective line, which you can decompose as the constant functions, one-dimensional representation, plus something else that is called the Steinberg representation with a dimension q. But then you can twist by another character of a character of G, and you get those representations up to twist. Then you get all the other representations when chi is not trivial or not fixed by S2, and in this case, the parabolic induction here is itself irreducible. So if you sum and simplify, when you do this exercise, you sum and simplify all the parabolic inductions, which are most of the time irreducible, I mean generically reducible, except when you're in that kind of situation. All possible chi's. And in this way, you get, you get q minus 1 times, you get q minus 1 twist of the constant representation, q minus 1 twists of the Steinberg representation, plus you get q minus 1 times q minus 2 over 2 classes of irreducible principal series representation, and you get to the conclusion that there are some representation missing. How many of them there are? Because of the conjugacy classes in G. And how do you obtain them? Well, you obtain them by inducing certain characters indecomposable of a non-split torus, meaning of FQ square star that you see inside of G. And those representations, those irreducible representations, which I'm not going to describe, are called cuspidal. And there are q times q minus 1 over 2 of them, which is exactly the number of degree 2 reducible polynomials with coefficient in fq, meaning that the cuspidal representations have something to do with the ways you can produce a quadratic extension of fq by using one of those polynomials. So here we start hinting at this, the idea that if later in the p-adic case, if we want to understand local Langlands correspondence, which can be seen as a higher dimensional local class field theory, we want to understand the cuspidal representations here in some way. In the finite case, there is something about it that the cuspidal representations have something to do with the quadratic extension of QP, so they sort of carry some arithmetic information. Okay, so that's something cuspidal or supracuspidal or suprasingular. That's something we want to aim at, or at least maybe define in the case of the representation of G and not bold G a little later. So that was my second point 2 when R equals C inside of the section representation of the finite group. So I'm going to finish this section by saying a word about the case of FP bar representations. Oh, okay. Well, remember that we had this lemma in the introduction that said that a P group acting on a mod P vector space has a non-fixed and non-trivial fixed vector. So if I take V non-trivial in the category of representations of G, so we said that a P group acts such that there is a non-zero fixed vector, so VU is non-zero all the time. So it means that I'm always in this situation here. So I can again do this whole thing, which is just an algebraic statement. So V, again, is a quotient of principal series representation. So you can classify the representation by semi-simplifying the principal series representations. A remark, in mod P, because we don't have this argument over there, these functors are not equivalences of categories anymore. Turns out that it's a little bit of a miracle, but they still give you bijections between irreducible. So you can also classify the mod P, the irreducible mod P representation of the finite group by looking at Hecke modules. But I haven't talked about it. I haven't proved at all, or I've given an idea of how you prove this here. Let's say that all we know at this point is that to find those representations, I have to classify the principal series to semi-simplify the principal series representations. And as a general philosophy, we can say that it looks like mod P, at least for the finite case, there is no cuspidal representation. So in some way, it seems like there is no hint as a potential Langlands correspondence mod P, but obviously things get more interesting when we pass from the finite group to the p-adic group. And I start, I guess, next time by explaining that in the p-adic case we have two kinds of inductions, and tell you a little bit what is known about this mod P Langlands correspondence. And my main point is going to be describing the coefficient system on the building and homological properties of the categories. Well, I guess I have to stop here.